All right, so we were in class, we were looking at span, and then we got this theorem that said the span of a set of vectors in a vector space is a subspace of that vector space. And we hadn't yet talked about subspaces, so I didn't do the proof, but I'm going to do it now. So the subspace theorem tells us that if I want to show something is a subspace, I got to show it's not empty. It's not the empty set. I've got to show it's closed under the addition from my vector space, and I got to show it's closed under the scalar multiplication from my vector space. So let's think about why this thing is non-empty. Well, if I take 1 times v1 plus 0 v2 plus 0 v3 plus blah, 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 or even if I take 0 times all of these, that's even easier. Let's take all of our vectors, scale them by 0. One of the properties of vector spaces that we proved was that when you multiply a vector by 0, you get the 0 vector. And so we are just adding up a bunch of 0 vectors, which is 0. And that means that 0 is an element of the span of S. Oh man, and I've got a typo here. I don't want to show S is not empty. I want to show the span of S is not empty. It turns out S is not empty itself, but the span is also not empty. So we get there's an element in here. And span of S. Therefore, it's not empty. Sweet. So spans, as long as we're, like I guess you could try to span the empty set, but that would be kind of silly. So when we take the span of a non-empty set of vectors, we get a non-empty set. Okay, I want to show this is closed under addition from B. So let's let U and W be elements of the span of S. And then I'm going to add them together. So U plus W, well, U is a span of vectors. So they're going to exist A1, V1. Or sorry, there's going to be A1 and A2 up through AK that are real numbers, where that's my U, right? So that's going to be my U. So there exist A1 through AK, and also B1 through BK, where this guy is U, and the next one is going to be W. So B1, V1, plus B2, V2, plus blah, 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 plus BK, VK. That's my W. And what I get is a new linear combination. I get A1, B1 times V1 plus ... up to AK plus BK times VK, which is an element of the span of S because all of these are real numbers. So that's a real number scalar, that's a real number scalar. So that tells me that my addition is closed. When I take sums of linear combinations of vectors that I built from S, then I get a new linear combination of those vectors where I just combine like terms essentially. It's sort of, like all the coefficients for the V1s get pulled together and for the V2s get pulled together. Same kind of thing for closure under scalar multiplication. Let's let C be an element of the real numbers, and we'll keep U in span S, which means that there are A1 through AK where U is A1, V1 plus blah, 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 just like it was above, AK, BK. Then if we look at C times U, we're going to get C A1, V1 plus A2, V2 plus blah, 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 plus AK, BK. And you know what I'm about to do. I'm going to distribute that C. So get C A1, V1 plus C A2, V2 plus blah, 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 plus C AK, BK. And that's also in span S because each of these scalars or the products of these scalars, C and A1, that's a real number. C times A2, also a real number. C times AK, also a real number. So I get a new linear combination of V1 through VK when I scale by C. And so this is now legitimately a proof sketch, call that a sketch up top, that shows why the span of a non-empty set of vectors in a vector space is a subspace of that vector space. And that's an application of our subspace theorem. Imagine with horror what would happen if we had tried to prove all 10 things to show something as a vector space. That would have been true misery. Even I, someone who enjoys math, would have been quite miserable doing that. So let's just draw a little heart here for the subspace theorem, because it made our life a lot easier in this proof, and will continue to do so for the rest of the semester.